Okay, let's get started. Welcome to the software and tools for data analysis session. My name is Andrew Sterner. I am a program manager for the LSST Discovery Alliance. Before we get going, reminder that there's a Slack channel where you can put your notes or questions in real time, whether you are here in person or on Zoom. We will have a community conversation sort of similar to how we did yesterday with the undergraduate panel workshop. So there is a live notes document if you want to attend, particularly for those are on Zoom to record your thoughts there. So a few reminders at the beginning, right? We have our code of conduct. If there are any, if you notice any violations of the code of conduct, please see the code of conduct contacts that are listed here. Please keep continuing to uphold this community of trust and respect that we have for each other. And for those that are presenting online or joining us online, please, if you're not speaking, please stay muted. And if there's other questions, the Slack channel is available for that. Okay, so the session goals for what we're trying to do here, right? Rubin data is here, right? And there's a lot more coming. DP0, or as you know, it was already been created, but now we have DP1 on the order of gigabytes to terabytes, sort of in terms of the total scale. But we're about to sort of jump into DP2 and DR1, which gets to be much larger data packages. And so with the paradigms that we have, be able to do science on our own machines, maybe on a shared machine for your research group. To now with the realm of the amount of data volume that we have coming to us, right, is going to change dramatically. And so in order to do that science, things are going to have to change, whether through tools like the Link Frameworks softwares are building, through using expertise from the field of private industry that Project Dovetail is working to bring to our community. We are entering this new era. And so the goals of this session are to think about what existing software tools there are, sharing plans for what future resources we might need or have planned or will need, and then also identifying near and long-term goals from the community. So with that, we will get started with our talk. So the first talk is from Jeremy Kubica of the Link Frameworks team, talking about the DP1 update.
Hello, I am Jeremy. I am the engineering manager of the Link Frameworks team. Today I'm going to be talking.
Excuse me, but the remote people can't see the slides.
Oh.
There we go. Thank you.
Thank you. All right. So today I'm going to be talking about what Link Frameworks has been up to for about the past 6 months, focusing primarily on things that touch DP1 data. This is going to be an overview. We've got a lot of projects. I only have 15 minutes, so I'm going to just touch on some highlights. All right. For those of you who don't know the Link Frameworks team, we're a multidisciplinary team. Our mission is to try to enable Rubin science by developing scalable and productionized software and algorithms in collaboration with the Rubin community. And generally what this means is we're looking for projects that we believe will be impactful to a broad range of astronomers. We're really trying to benefit a lot of people at once, and work on top of existing Rubin tools. There's been a lot of investment in the DM pipeline and everything like that. And we want to build and augment on top of that. We want to be collaborative and avoid unnecessary duplication. We don't want to reinvent the wheel wherever possible. The team tends to focus on things that have engineering challenges, specifically productionization, acceleration, scalability, and usability as well. Everything we do is open source, so it can be used by the broad community. It's primarily focused on Rubin, but hopefully generally usable. The team, as I said, is a multidisciplinary team. We have research scientists who are astronomers, and we have software engineers who are largely from industry, and we brought them in to bring in industry experience and best practices. We're distributed over 2 sites, half at the University of Washington, where the PI is Andy Connolly, and half at Carnegie Mellon, where the PI is Rachel Mandelbaum. And you can see the full list of people here. And then, of course, we work very closely with the LSSTDA. All right, we've got a bunch of projects. I'm going to talk about the ones at a very high level that have the red stars next to them today. I'm not going to talk about the incubator projects. We kind of have 2 types of projects. One is these core long-running projects that we work on for a while and continue year to year. And the other one is incubators, which are very focused 3-month collaborations with groups outside of our own team to solve specific problems. I have a lot of cool stories from them. Unfortunately, I don't have time today. So instead, I'm going to focus on 4 of the projects, 4 of our core projects. But I'm happy, and I'm happy to also volunteer other people on my team to talk about any of our projects when you get a chance. And we'll have some posters at the poster session that I'll point to as well. So the first project I'm going to talk about is LSDB. This might be something that you have heard a few times in other talks. This is a framework for scalable spatial analysis. And there's really 2 components. There's HATS, which is a format for storing data in a way that facilitates spatial analysis and facilitates efficient access. And this is basically taking data, catalog data, and partitioning it up into files that roughly have the same size or the same number of objects at least. So that way they can then be distributed and processed in parallel. And we use HEALPIX as a scheme for dividing them up, and it's an adaptive scheme, so that way in areas of the sky where there are more objects, like the galactic bulge, we partition finer and finer to keep the file sizes about the same. And then by using spatial structure, there's a whole bunch of computations and analyses that we can facilitate doing very fast. The original motivation for this was cross-matching, taking 2 catalogs and finding out where they match. LSDB is a framework, the overarching framework that provides this distributed computation. It provides a pandas-like interface. It's built with Dask, where you provide queries, you provide different interactions, and it will build up a distributed graph and kick that off on multiple machines or multiple processes. And it uses HATS as kind of the foundational storage. So probably the biggest thing that we've done with LSDB and HATS is make DP1 available in it with additional structure and data. So we've been working very close with the RubenDM team in commissioning to make sure that we could import data into the HATS format. It is available. There's 2 links down at the bottom, and I believe these slides are available on the Slack channel. The data is, again, meant for efficient access, efficient distributed computation. As part of that, we organize the data by object or by source, so the light curves are kind of inherently part of the structure. In addition, we've added some information like PhotoZs that we've computed, and all this is available now on the RSP. We also took the early data, DP1, and actually ran time analysis to see what we could find. And we found a series of known and new transient and variable objects using this. DP1 is relatively small compared to what we're going to see. So we didn't get to stress test as much of the scalability as we will in later data releases, but we did get to actually see that we can find new variable objects using these. Melissa, who is sitting up and we'll be talking shortly, has a poster about this work, and we'll be talking about it throughout the day. So talk to her. And there's a paper on arXiv about some of the new stuff that we found. One of the most exciting things for us is trying to make sure we enable science and provide tools that more than we use. They're generally useful for the community. We were very excited to see that within the past couple of weeks, we've seen a bunch of papers. These are the ones we know about that use LSDB or HATS as part of the analysis. And so we're glad to see it's being used. We actually had a hack day earlier in the session where we featured LSDB and got to work with some of the people who are sitting in this very room. And we're happy to help you continue to use it and ramp up on it if it would be useful for your research. Another thing we've been working on with early DP1 data is photometric redshift. So this is actually a desk project. Rail is a framework for doing many photometric redshift estimation algorithms in parallel. So that way you can evaluate, compare, and get multiple redshift estimates. We've been working on running through the DP1 data to confirm that we can produce redshifts for the actual production data. So Rail will be used going forward. These are available. There's a tech note about how they were generated, and the data is now available in a variety of formats. We have RSP, file and NERSC, LSDB, et cetera. You can see there. And we're looking at taking the fundamental component of Rail, which is producing PDFs of the estimates, and actually bringing that into LSDB. So it's just part of the inherent data format. We actually have someone working on that this summer. A newer project that we're working on is time domain simulation. So TD-Astro is the name of the project, and this is a framework for simulating things under realistic noise and observational cadence. So doing things like selection function analysis, population studies, that sort of thing. The goal is really to be pluggable, modular, so people can easily add their own models, their own effects, their own whatever they want to simulate. And you can see kind of a general flow here in the types of data we produce here. In this case, we benefited from DP1 pretty significantly because it gave us a chance to say, is what we're simulating similar to what we're actually seeing? So to actually verify the simulation pipeline kind of going the other direction. So on the left, you can see a simulated DP1 light curve for a supernova type 1A. On the right, you can see a light curve of a new object we found that we aren't actually sure is a type 1A. So although the curves match, they might not be the same objects, but the important thing is getting the cadence and getting the noise properties similar and correct. So that way we know that what we're simulating is accurate. One of the things we've been happy to help with is we've been working with the commissioning team through to make sure that all of the tools not only work on the commissioning data, but we can use them as a step in verifying the commissioning data. So during commissioning, we were running through things in HATS format just to check to make sure we could import things. And it actually produced a pretty nice iteration cycle where occasionally there would be problems that arise in the DM pipeline in terms of data being missing or something that we could help identify and loop back on. And same thing for PhotoZ. It was able to be part of the commissioning process in terms of working out bugs. So the data is going to get a lot larger. And while that is exciting to me, I personally am a huge fan of making things scalable and making things fast. There is a general rule of thumb that I have seen throughout my career that when you increase the volume of data by twofold, your architecture tends to hit a new bottleneck that you didn't previously anticipate. So as we look forward past DP1 to DR1, which will have a much larger volume of data, we're going to uncover new bottlenecks. So the challenges we're expecting to face, both in our system and in other software systems, is just novel bottlenecks that come up as we start to increase the volume of data. We're also going to see new types of volume scaling issues. For example, if you're doing any sort of anomaly detection, the false positive rate is going to go up, or well, the false positive rate is going to potentially stay the same, but the number of false positives you see goes up with the data just because you're going to have more observations. And this is going to require new techniques to handle that level of scalability. And then finally, probably the thing I'm most excited about is the questions people haven't even come up with yet. The questions that once people start doing the current analyses with the data, they're like, wait, what if I looked at it in this way? And what that will require in terms of computational techniques and computational methods. So we've got a lot of exciting stuff in front of us. We're hoping to work with as many of you as possible. So if you have problems that you think have software components, please come talk to us. We have our software, as I said, I kind of flew through at a very high level. We have documentation. It's on the LSSTDA site. If you just go to the link framework subsection area focus, you can find all of the read the docs, all of the code, or you can come talk to myself, Melissa, Nevin, Andy. I think that's everyone in the room. There's a couple other people here, Alex as well. All right, thank you. Any questions?
Jeremy, are there any questions in the room? Yes, great.
Hi, thank you so much. This is Erin Clark. I'm kind of wondering, you kind of mentioned towards the end of your talk about your false positive rate maybe not changing, but the number of false positives increasing. I'm kind of wondering if you could expand maybe on the techniques that you are exploring to minimize that.
We're looking at a variety of techniques. One, I'll talk about one specific case, which is not something I talked about today, but I think illustrates very well the false positive rate. So one of the projects we work on is moving object detection for very faint objects. So we have an algorithm called KB-mod, which does looks for objects out TNOs, which are very faint. And it has a false positive rate. You have stars, you have artifacts, things that look like they could be objects. So one, we're using a bunch of different approaches for it. Some of it is just better filtering algorithms of just trying to use filtering statistic techniques. We're using machine learning models to try to get down the rate, and then building tools so humans can more efficiently be in the loop. So we kind of have a three-prong approach. Out of those, we honestly expect the machine learning models to be the most impactful and to help us scale the most, but that's kind of what we're thinking.
Okay, we have time for one more question.
Hi, this is Adam Thornton. I work on the RSP. Who is in charge of docs.lsdb.io? Because I have a couple of suggestions for him, that's all.
You've got two people here who you could talk to. Melissa sitting right there and Nevin right there. And both seem to be like both kind of volunteered and raised their hands and look excited. So please talk to one of the two of them.
Great. Let's thank Jeremy again. Our next speaker is Aritra Ghosh, who should be joining us virtually. So Aritra, if you'd like to share your screen.
Can you folks see my slides?
Yes, there we go. Get started. Go ahead.
Should I start, Andrew?
Good.
Okay. Hello, everyone.
Yes, go ahead.
Hello, everyone. I'm Aritra Ghosh. I'm a Catalyst Fellow at the University of Washington, and today I'm going to be talking to all of you about Hyrax, which is a new machine learning framework for scalable machine learning and unsupervised discovery with large surveys that we have been working on along with the Link Frameworks team. And let me kind of start by giving an overview of why we went ahead and went down this pathway of developing Hyrax and what it is. So I'm sure all of you are familiar with this image. This is just a small section of Rubin's view of the Virgo cluster, which was released as part of the first look images. And what this image is pretty good at showing is in terms of extragalactic science, the variety that is there out there in the cosmos. And it also shows kind of the richness of the Rubin data. And as you all know, in addition to Rubin, there are many surveys which are coming online, which will be some of the most information-rich surveys that we have ever taken. And as we have moved on towards this regime of very large surveys, astronomers have turned to using machine learning more and more in order to keep up with this volume of data. This plot over here shows data from ADS, where refereed journal papers for astronomy journals. You kind of see the growth in papers which have either machine learning, neural network, or any of these terms mentioned somewhere in their abstract or their title. So clearly, a lot of us are using these tools in order to keep up with these data volumes. But if you take a look at the typical machine learning workflow in astronomy, this is how it typically goes. You have your big survey data server. You use some catalog to identify sources and download data from that server. You do some data cleaning and pre-processing, and then you go ahead and apply your science model onto that data. And once you have applied your science model, you get some outputs or something that you're predicting with your science model. And then you go ahead and write a paper. So that kind of gives you kind of the typical machine learning workflow. But right now, there are kind of many bottlenecks in this workflow, which pop up, especially for large data sets. And doing projects like this typically demand coding effort, which goes beyond what is typically taught in astronomy. So this can be anything to do with loading of large numbers of vectors, multiple GPU task distribution, being able to explore latent spaces interactively or in any other fashion. And currently, each research group typically just develops its own bespoke solution, which can be challenging, and it leads to a high training and maintenance overhead for both students and developers. So essentially, HYRAX is just an answer to that. The quickest way to describe HYRAX is essentially there's a bunch of these different tasks that you typically have to care about when you are doing a machine learning project. They're all from data acquisition, hyperparameter tuning, latent space exploration tools, all of this. So what HYRAX does is it takes care of all these kind of things at the outskirts for you, while you can focus on just writing your machine learning model code. So you can think about it as something which makes your life a lot easier when you're trying to do these machine learning tasks. Now, HYRAX, as I pointed out, there's these kind of, the typical workflow has these kind of 4 steps, any machine learning workflow. What HYRAX does is it kind of transports these 4 steps into 4 different modules within HYRAX. So what you can do is it has a download module with which you can download data. The Rubin version of this doesn't really download the data. You can just directly stream from the butler to your models without local storage. And you prepare the dataset, you pre-process it, and then you train. In order to just illustrate how simple it is to train models using HYRAX, this is all the code it takes for me to train a very simple autoencoder on a subpart of Rubin DP1. And once you train your model, so first let's talk about this supervised part of the work chain. When you train a model, what you typically get is essentially this view of all the different models that you have trained. You can sort things by their loss function. So it gives you a nice kind of visual outlook of all your models. You get a quick view of how your different models compare in terms of the loss values they achieve. And also you have a quick way of logging any other different metrics that you might care about, either to do with your system or with your model or anything else. So that's kind of what you do once you have trained a model. So that's like the model comparison piece. And once you have done that, the next step is you go ahead and infer. And that kind of completes this supervised part of the workflow, which is up there. Another option is unsupervised discovery or unsupervised machine learning. And there you need a few other components in addition to what I showed you. And there HYRAX gives you 2 additional things. One is a database. So essentially, it builds up an efficient vector database for storing latent space embeddings of these different kind of surveys that you're trying to embed. which is fast to query, and you can perform similarity searches. And you can also get this visualize module, which allows you to kind of explore these embeddings in an interactive fashion. And what we have done with Hyrax is essentially we have started with a set of 5 projects, which are shown here on the left. As you will see, the projects are very different and they cover very different scientific domains. And that the primary reason I'm bringing that up, it kind of shows you how diverse the different science cases are that you can tackle using a single framework. In my last couple of minutes, I will just end with kind of a little bit of what we have been doing, this unsupervised discovery in large imaging surveys. And that's has been one of the primary pushes of what the Hyrax team has been doing. And the basic idea goes like this. Let's say you have cutouts from your survey of choice. You have these variety of different tasks that you want to do. You want to subcharacterize, identify mergers, you identify rare objects, identify anomalous sources, you want to do image similarity search. One way to do this is essentially just build up a latent space where hopefully these different types of objects are clustering together in different parts of this latent space. And one way we have been doing this is using a bunch of different deep learning algorithms and different subclasses of these algorithms. So unsupervised algorithms, self-supervised algorithms, contrastive learning algorithms, and astronomy foundation models in order to build collections of many collections in different types of these latent spaces and try to figure out which latent space and which kind of model is good for what task. And we have been doing this with 3 different students for 3 different surveys, a mixture of both simulated data and real data. And part of that data is DP1. And let me just end with kind of one kind of little snippet of what the DP1, like the Hyrax tools, what they look like when you visualize them with DP1. For example, this is a latent space model that you can build, that we built with ECDFS DP1 data. And what this 3D visualization tool allows you to do is you kind of go in, you can play around with different parts of the latent space. You can color the latent space according to different kind of the different values that you have in your catalog and change color maps. And then once you kind of want to poke around a little bit more, you can go ahead and select subparts of that latent space in order to both visualize them and look at what parameters are ending up in your different portions of that latent space. You will see I go ahead and select that box, and you'll see this part typically seems to have a lot of extended sources, a lot of disk-dominated stuff, and you can also on the top left look at the properties of your selected objects. Since I'm out of time, I will save the rest of my slides for the DP1 show and tell later today. Well, I will show a little bit more of our results from DP1, but I will put up my summary slides over here, and I'm happy to take any questions that you might have.
Great. Thank you, Richa. Are there any questions? Yes, we have some questions in the room. We have time for about 1 question.
Thanks. Oh yeah, that is on. Thanks for an interesting presentation. I'm curious, as I'm sure you know better than I do, this is a very, especially the model building part is a very active area of research right now. Can you say if and how you plan to sort of keep up with that, especially on sort of the decade-long lifespan of LSST and Rubin?
So I'm assuming you're talking about the different, like the fact that every few years people come up with new sorts of models that they want to try on data?
Exactly.
Okay, so that's the nice thing about Hyrax's design is you actually bring the models to us. So when I showed that little diagram of all the things that we take care of you, we expect you to bring your model to us in PyTorch, that you bring us a PyTorch function which describes your model. So we'll keep up with a set of models that we inherently natively provide. But what makes Hyrax kind of more extensible is you don't really need to use the models that we provide. You can bring any PyTorch model to us. PyTorch is the only dependency that we have. And as long as it's writable in PyTorch, you can just run it within Hyrax. So I think making it extensible in that way is our kind of primary way of making sure it keeps working with newer models.
Thank you, Aritra. Let's thank Aritra one more time. Our next talk is going to be by Destry Saul. And let me get to it. Start talking.
Hello? Yep. Excuse me. Hi, my name is Destry Saul. I'm the managing director for Project Dovetail. It's a new model, a new program that we just are getting started with, intended to bring more software engineering expertise into astronomy generally. The line we have here is Project Dovetail provides targeted software engineering support to accelerate science and something. Sorry, killing me. What's the rest of it? And and launch discoveries that otherwise would not have been made. The engagements, how that works is an engagement starts with a consultation, some one-on-one time to talk with someone, because we understand that not everyone knows what they need. They don't know what they don't know yet. And then once we've identified what help you could have, we bring in engineers, and they have a managed experience where they help you out. Can we make this any bigger? I'm sorry, I'm losing my place here. So that's a nice way to, that's a nice wordy thing to say. But what is it really is, so we're a services project organization. Sorry, you okay? Okay, there we go. Okay. So that's very different from like the Link Frameworks team. So Link Frameworks and these other projects build products. So you're building a framework, you're building a library. You're killing me. Okay. There we go. So then what are we seeing up? Oh, this is not plugged into the projector. There we go. There we go. We are. We're sharing on my personal computer. Sharing the personal projected. Okay, we're good? Great. Okay, so going back, we're a services group, not a products group. That's different than what most people have run into, I think, generally in astronomy. So that means we are not building libraries and maintaining those libraries. Can you full screen this? Is that any better? Sorry about that. Okay. So we are not building libraries or building products or building applications that we are designing and building and delivering. We are helping people who are building those libraries, or helping individuals who are doing research by providing labor, advice, those sorts of things. When our engagement's done, we go away. So it's very important to have teams like Link Frameworks and all the groups out there. We are a very complementary and different group. So what that means is we're bringing together 4 distinct groups of people. We have the Discovery Alliance, which is providing our administration, our connections, the global reach, all of the great things that Discovery Alliance does. We have professional software engineers. So this is specialized experience. People with many, many years of experience coming in doing projects. We have a group of astronomers turned software engineers. So this is another thing that's kind of unique to our program. So ex-astronomers who have gone out and done industry that play translator between astronomy groups and the professional software engineers who don't have any astronomy experience. That's an important part. And then the astronomers, the scientists, the people who say, this is what I need to do, please help me make that possible or make that faster, et cetera, et cetera. A big bullet point for me is we don't do science. This is like the one thing we do not do. If you want us to help you with your error analysis or your scientific algorithm-y things, we don't do that. We are non-astronomer software engineers. That's what we're bringing. We're here to help you do more, better, faster science, not do the science for you. Is this one? Yeah, there we go. Okay. So I think the best way to really sort of drive this home is just what are we doing? Here are a bunch of examples. The ones with stars are things we are either currently doing or are on our roadmap for folks. The first one, just discovery, sit with you, help you figure out what you need, what you don't know, what's possible out there. Code audits, project audits, let us dig through your stuff and let you know how it could be better. Turning your code into an open source library for others to use. I like this one a lot personally, is you have a bunch of code, you're ready to publish a paper. The code's not really in a nice place, maybe not great reproducible. You'd sure like it to look better before you put it out there for everybody to see it. We can help with that cleanup. That updating old code, this is another fun one that we've had, is you've got an old Python 2 tool. It's dead now. It needs to be something else. Throw it at us. We can be very quick about it and get you a working tool right away. Converting notebooks into CLIs. That's another one that we've had. Some of these other ones, I'm not going to read all of them, but another thing is we're available for projects on 10-hour timescales. This is not huge projects, right? We can go down to, you just need a couple of hours of help getting something onto GitHub. You just need a little bit of help with your versioning, those sorts of things. Even debugging help, pair programming. I can bring you someone for 10 hours to just hang out for a day and watch your code and give you some tips. That's how a lot of us have learned in industry, is working with people who are better and more experienced than us. So we want to make that available to people. Down here at the bottom, I know data science and AI guidance. If you want consulting time from professionals who work in those spaces, we have access to those folks. There we go. So here's some frequently asked questions as well. These are actual questions that I have gotten. I did not make these up. This is too good to be true. It's not a question. It's also, I don't have an answer for it. It is. It's exactly what it is. Come talk to me. I will talk to you about it. We are real. Where do I send my proposal? You don't. This is another big difference in our program, is we're coming out to you. All you need to do is, literally send me a text message, send me an email. I will come and talk to you. We will figure out what to do. We don't need proposals. Why hasn't this existed before? The Discovery Alliance, I give great credit for vision and resources and agility. We don't need to go through mountains and mountains of paperwork to get this started. We're just starting, which is pretty fantastic. The other thing is these ex-astronomer solution architects are more available. There are now lots of us who have left the field, worked for 10 years, and are now interested in doing good for science. That's my background, by the way, in case I didn't mention that at the beginning. Got my PhD, did about 10 years in industry. Now I'm trying to do different things. Also, with the pandemic, there's a lot more remote workers out there, and the Discovery Alliance is uniquely available to hire and pay people globally. So we can work with anyone in the world, pretty much, on both sides of that equation. And a lot of people, there's been a big shift also in the tech industry of trying to give back, trying to do good, trying to do science, trying to not just make widgets all day. Another question I've had is, how is this different than Link Frameworks? How is this different than this center, this other thing, this consulting group, et cetera, et cetera? Again, services, not products. We provide labor. Specialized contractors, this is a big one that relates to my next point, is because we are working on smaller engagements, we don't need to hire generalists. We can hire people that really know that one thing a lot, as opposed to when you need to hire a group, you need to cover all your bases with 5 people. We don't have that constraint. And again, one of the special sauce bits is these translators who can sit down and speak astronomy and sit down and speak tech, industry tech, and make that work. Because we have heard plenty of feedback on people who have tried to do that, and there's just sometimes a mismatch of jargon or priorities or et cetera. And so we're smoothing that out. Another one is, why shouldn't I just hire someone? Why do I need to talk to you guys? I want to say really clearly, we are not trying to replace anyone. If you can and have the ability to hire a software engineer, you should do that. I was a software engineer in an astronomy space. We need more of them. If anything, I want to show people that hiring software engineers is useful and a net gain for their groups. But it's not always the right solution, like some organizations can't afford to, especially a full-time developer. Then you have all sorts of overheads that you have to deal with on that. Or maybe you don't need someone for a long time, maybe like you're working on a project and then they need to go away. But if you hire someone full-time, there's lots of cons to hiring, even if you can. And lastly, this is one I've heard a lot of times, is I don't believe these software engineers exist. Where are they? How could you find them? What? And my answer is, well, 1, trust me, they do. And 2, I want to introduce our new engineering manager that we got. This is Adam Seaver, and I'm going to pass to him.
Hi, everyone. I'm Adam Seaver. I'm an engineering manager. I've worked in the tech industry for 25 years, and I can easily confirm the unbounded enthusiasm for, to help out with a science project. What could be cooler than that? I think the times in which engineers may hesitate or struggle to be successful fall into a few categories. They are looking for projects that are well-structured, have good milestones. A finish line at the end is critically important. I think they've been roped into eternal projects that may slow them down. Also, to have the jargon translated in such a way that they can take ownership over what they're building is critically important, both for them as well as for the output of the software that they're going to develop. And so finally, the ability to understand how their contribution fits into the larger piece that actually is advancing the science. I think that's really what gets industry engineers excited to commit their time and to be involved. And that is the special sauce that the solution architects are bringing to Project Dovetail. And I think that's what really is what makes it successful that way.
So to wrap up, we're currently working on bringing in funding to do more bigger projects. We currently have enough funding to do small pro bono projects. That's right, pro bono. That means you don't pay us. We just do work for you. Again, too good to be true, but it's real. Again, at the 10 to 20 hour scale. Yeah, again, we want to scale up and out and do more small projects and more bigger projects. I think there is, again, infinite work. Everyone I talk to has something that we could do that could help them in some way. If you don't believe me, come talk to me. Again, please come talk to me. That's basically, send me an email. That's my email. Come find me. I'm happy to talk to anyone. And we're going to be hanging around for lunch today. So there we go. Questions? Great.
Here we go.
At the SET Institute in Silicon Valley had a program called FDL, Frontier Development Lab, which basically your idea, give, computer science background or engineers to do astronomy program. Those NASA proposal calls, supported by all high-tech companies. It's like summer programs they had. They stopped this year because funding, but they will be back as a space science artificial AI lab. So, any of your company people or scientists who want to do, those connected with high-tech company can apply, and we basically scientists give the idea, and engineers or summertime they made a group like all 9 and solve that, very skillful programs to 3D movies and many things. Okay.
Cool. I'd love hearing about these other. There's a surprising number of centers that have collected folks and are trying to do exactly that. So awesome. Thank you.
I have one more question. Oh, I guess you.
Meg Schwam, Queen's University Belfast. I think this is great. I got the comment and question thing, unfortunately. One thing is that on the LSST-DA website, my understanding was it said that Project Dovetail was only available to those that were actually LSST-DA member institutions. So it sounds like that isn't the case anymore. So we get to get clarity on that point. The other thing, I guess my question is given there's so much that could be done, and us as a community who are trying to think about all the millions of things we're supposed to be doing and getting ready for LSST data, how do you think we can communicate with you or find out what are the possibilities of what you can do for us in sort of an easy way that makes it easy for us to decide whether or not this is a useful pathway? Because I found for at least the Link Frameworks incubators, the office hours is actually where I found that my proposal wasn't quite fit, but people were excited about it. And I was like, all right, I'll put in a proposal. So I'm just wondering, as you have thoughts of, yeah, I can email you, but I don't even necessarily will know the words to say. So just wondering if you have thoughts about how, what ways we can all talk to each other that might be useful, or things as wearing my science collaboration hat, co-chair hat on it. What can I do to help encourage my science collaboration to figure out what could be done?
Right. I'm going to start with your last bit first, which was you don't know what you need to know. That's fine. That is exactly what I assume is the case. So the emailing me is literally just, hi, can I talk to you? Let's talk through what my thing is, because I found that, in a half an hour, we can probably find, the way to frame it, the way to say it. About it being member institutions. Yeah. I'm not sure is the answer. Okay, sorry.
Hey, yeah, thanks, Meg. And the thing that is posted on the website is referring very specifically to this exploratory, it's not even it's an exploratory pilot right now. And so in the limit of limited resources, then we would prioritize requests from member institutions. And thus far, the extremely limited resources we have are getting fully subscribed by those requests. That said, right now, if a non-member institution has resources themselves to have an engagement, then we would be open to support that. And reaching out to Destry and Adam to scope out what are the possibilities to make a plan and say, when you're ready, let's do this. That 100% can be done right now. Is that fair, Destry? Is that consistent with how you're implementing? Yeah. Thank you, Meg.
Let's thank Destry one more time.
You left Zoom right? Yes. All right, so where's the probably the tab on
Claudio Lopez, you are the next speaker who is virtual. Are you able to share your screen?
Okay, yeah, I'm here. Can you hear me well, Andrew?
Yes.
Okay.
Give us one moment though to work out some Zoom.
Okay.
Did you want to share your slides
Yes.
with yeah, that would be the easiest.
Okay, give me a second. So. Can you see the slides?
Yes, that's working. Great.
Okay.
Thank you. Go ahead.
Thank you, Andrew. So, hi everyone. I'm Claudio Lopez. I'm from the ICATE Institute, San Juan, Argentina. And today I'm going to present you Sky Katana, a new Python tool we have developed under the LINC Frameworks project, which you can use to create Angular masks for large surveys. And I will show you how we apply the Sky Katana to the LSST data preview 1. And for this, we will use the Chandra field. Sky Katana builds on 3 core packages, Hillsparse for sparse helpix handling, so we don't need to store every pixel, MockPy for multi-order coverage maps and precise region definitions, and HATS developed by the LINC team, which tile catalogs into multi-resolution helpix cells for efficient spatial queries. So Sky Katana works as a pipeline of Boolean Hillsparse maps, creating a mask at each stage. Some of these stages are the footprint from the input catalog, a whole map of exclusion circles around stars, an extended mask for nearby galaxies, property maps, which allow you to obtain a map adapted to a property map, which this stage you can obtain uniform depth regions, for example, and user-defined exclusion zones, among others. The last stage is merging all these into a single Hillsparse Angular mask. Once merged, you can generate random points within the mask or filter a catalog to retain only sources inside it. And you can even combine masks from different surveys to find the overlapping area. For our Chandra field demonstration, we begin by plotting all LSST DP1 Chandra sources in a blue on a Radek map. And below that, we display a histogram of Gaia G magnitudes in the same field because we use Gaia to find an expression that establishes the size to exclude in each star. In our example, we use WISE to show you how to combine 2 surveys in one mask. We extract optical ghost, halos, and spike from WISE to pixelize them as a second mask that can be combined with the Chandra field. We derive the exclusion radius by grouping Gaia stars per bin of magnitude, computing the local density inside concentric circles of increasing radius, as we show in the animation, normalizing by the mean density of the full Chandra field, and recording the radius at which the normalized density reaches 90%. Repeating this for each bin give us a radius magnitude relation, which we then use to set the appropriate circular mask for every star. To count sources around star, we use our Gundam package, which is useful for counting pairs of objects at a given distance and for computing autocorrelation and cross-correlation functions. The radius Gaia magnitude plot shows a clear power law trend for magnitudes brighter than 17, flattering at less bright end. On the right, a real Chandra field image taken from the RSP overlaid with these circles, where each star has its own unique area. Plotting the fraction of area lost against the Gaia G magnitudes allow us to understand how stars of different brightnesses impact the final mask. This can help decide which magnitude cutoff to use when creating the mask, based on how much survey area you are willing to sacrifice. So we have everything we need to create a mask for the Chandra field. I have prepared a quick video showing how we use Sky Katana to generate this mask. I ran this notebook on the Rubin Science platform in the small configuration, 1 CPU and 4 GB of RAM. So first, we instantiate the pipeline by creating a new Sky mask pipe at order 16, the output order of the final mask. Next, we build the survey footprint mask from a HATS processed source catalog, which draws every observed pixels in the Chandra field. Each stage automatically reports the map's area in square degrees. Then we load a pre-computed property map that allows us to define a map with uniform depth up to magnitude 25 in the R band. After that, we subtract circular exclusion zones around Gaia stars by supplying their centers and radius. We found that 4 stars in the field have no Gaia magnitude measures, so we calculate their exclusion radius based on their local density and loaded them as user-defined areas. We then combine all components, keeping the uniform depth area and subtracting both Gaia and user holes. To inspect the result, we can print the pipeline object, the MKP object, which shows how many pixels make up the final mask, the total area in square degrees, and the pixel size in arc seconds. To visualize the mask, we plot 200,000 random points inside it with the excluded star circles overlaid in red. There. You can repeat the previous stage without applying the property map and plot a new mask. This take a few seconds. Okay, there you see. To integrate waste exclusion zones, we set up a secondary pipeline at order 12 and will its footprint create a new hole map to order 16 and use it as the new hole map of the Chandra pipeline. Reset the footprint to the previous final Chandra mask and repeat the whole masking stage using the WISE mask. Finally, we plot 500,000 points inside the combined Chandra WISE mask. And to filter our science catalog, we read the full HATS catalog, apply the final mask, and plot the remaining sources. So finally, we have a uniform deep star-free sample ready for work. So in summary, Sky Katana performed Boolean operation on Hillspar mask in seconds that results in masks that avoid multiple effects that affect observed detected objects, even those from more than one survey at a time. By following the link on the right, you can find the mask we created for Chandra field, both with and without the property map applied, and for several stellar magnitude limits. Looking ahead, we plan to apply Sky Katana to all 7 DP1 fields, finalize El Zorro, our civilian tool for multi-order mask, optimized for HATS and LSDB, and develop machine learning methods to avoid galactic cirrus regions. So thank you for listening. I hope you will start Sky Katana, try it out, and share your feedback. So now I'm ready to take your questions.
Thank you, Claudio. Are there questions in the room for Claudio? Okay, I'm going to ask the next question. So what do you, so you talked a little bit about the some of your initial plans. Can you say some more about what you're planning to do next? How will you change things with DP2?
Okay, with DP2, we want to work more with the approximation that we use to the fit that we use to the star mask, the bright star mask. And with that, we want to provide in our Sky Katana package a way to that the user can select the approximation that he wants to the bright star mask. Because after we plot, I can see you. I can show you here. Some of the radius of our mask are maybe bigger than we wanted, and in other cases are smaller. That is because we use that is for the approximation that we use, and this came from this 90% that we selected here. So we want to provide the user can select here a 90, 80, or another percent number to personalize his own bright star mask. And we choose this Chandra field because it's the deepest field right now, but we want to apply the other fields that DP1 has.
Very much. Let's thank Claudio one more time.
Okay, thank you. Thank you, Andrew.
Next speaker is Melissa DeLucchi, who will be talking about the Link Frameworks hackathon event.
Just double check. Just gotta talk louder, they'll hear you. Oh, the share. No, it's still sharing. Oh, I didn't. Okay.
All right, hopefully you can see the slides online now. I don't know if anybody's monitoring Slack to see if that's true. Awesome, great. So I will try to briefly go over this. Unfortunately, even the title is very long. We had a Link Framework software workshop just before the RCW, and so I wanted to give the hackathon post-event recap. I also wanted to, I added this slide in the last 5 minutes here, but slides don't progress. What? Gross. Okay. Yeah, so my interjection is that Destry's right. There are literally dozens of us at least. So I got my bachelor's in math and physics, did some astronomy research as an undergrad. I spent over a decade in software engineering industry, and now I'm here and I'm having a blast and it's a lot of fun. And I know that I hear actually that story quite a bit around. And so, yeah, there are more of us than you might imagine. So I wanted to talk a little bit about Link Frameworks and LSDB and TD Astro and our tools in DP1, the pre-work that we did for this hackathon, the results, the lessons learned. Just kidding, Jeremy talked about half of those things, so I don't have to. And for pre-work, the LSST Discovery Alliance, particularly Andrew Sterner and Hu Nguyen did an awesome job helping us get prepared for this hackathon. Really couldn't have done it without lots of people doing a lot of stuff. But one of the things for our participants that was really important was to have a formal application process. There were approvals, there was a deadline. I mean, we tried to take everybody who applied, but that applied some positive pressure to folks to actually apply. And you have to be pretty motivated to fill a form out ahead of time. And so that, yeah, gave us a pretty good selection bias, and we had a really great group of folks who did end up coming to the event. There was some travel funding that was provided so that we could, encourage that diversity of folks attending. There was coffee and there were snacks and there were meals for the duration. I think that was really important as well. Noir Lab was generous enough to provide us with some physical space. So we had a number of different conference rooms that people could break out into. And it was nice and comfortable. It was, I think, slightly warmer than it is in here, but I like it cold, that's okay. And as well, we just limited it to just the LSDB and TD Astro engineering teams. Jeremy mentioned that we have a handful of other projects that we're working on within Link Frameworks, but we kind of wanted to narrow our focus here. And so each of those engineering teams built some software tutorials and some sample hack proposals, just so that our participants could get an idea of what we imagined the appropriate scope would be for something that we could accomplish in a day and a half. Then we created a dedicated Slack channel, trying to drive some of that early engagement and get people to start thinking about their hack pitches, because they could see our examples and get a sense for who else might be attending and who could help them with their projects. So this is a repository that we created for LSDB. We also provided a needlessly detailed setup guide for how to get access to the RSP, particularly how to get LSDB working within the RSP. LSDB is now installed in the default RSP image. So really just needlessly detailed instructions. But we did have a lot of issues with that in previous hack sessions. So I think that proves that we're learning from these events and trying to do a little bit better job each time. TD Astro, this was their first hackathon that we had for that software product. So that team was charged with adding a handful of new tutorials and a glossary. We already had a handful of tutorials there, but just refining them, having folks run through them again and see what they could do to make them a little friendlier for the new audiences. And also some new overview materials and slides and assets, just stuff that's really exciting. And then we hacked. We got together. These are real candid shots. I don't think they were posed anyway. People are really doing work, having conversations, laughing, giggling. It's fantastic. So we ended up having 9 different projects split between TD Astro and LSDB. And I know that we are a little tight on time, so I won't go into all of them. Also, I didn't understand a lot of them, so that's okay. I don't have to talk about them. But we got some interesting light curves. looks like light curves. And so all these were simulated using the TD Astro package for new science use cases that we haven't tried within TD Astro before. And so that was very exciting, both for our team to get feedback and also for these science teams to really get started on collaborating with us and also getting started on their science with these forward modeling light curves. In LSDB, we also got some science and features. We had some folks who were attending who just wanted to, do some coding and write some features and get involved in the development process behind LSDB. And that was really fun because we had engineers who do that every day and we're happy to share. But then there was also some science that happened. And I'm very excited that we had one of our first solar system science use cases come in through LSDB. And those are times that you can look at 3i Atlas when there probably won't be any other stars around. So that's pretty cool. And in particular, TD Astro got a lot of feedback. So these are some issues that were opened and some of them are already closed. These are some pull requests that were created in response to that and some of them are already closed. And that was just very exciting to me. Every little bit of feedback that we get from our users is a beautiful gift and we really appreciate it. So what went well? A lot. I'm so excited. I had so much fun. We had a really great group of folks and we ended up with a really good variety in terms of a lot of dimensions and career level. We had undergrads, we had grad students, we had postdocs, we had faculty, we had everybody. In terms of how much Rubin involvement people have had before the event, people have been like, oh, Rubin, that's a thing, that's cool. Some people who've been around since the initial project proposals, and also scientific interest, AGNs, galaxies, things that are close by too. What also went well was trying to, again, make that smoother on-ramp for the environment setup so that once people came to the hackathon event, we could really just hit the ground running and start doing our science. I also think that the event being fully catered was a huge plus. That meant that we could just keep talking and keep hacking and didn't have to pause for an hour and a half to go walk and have lunch and then come back. That was immensely powerful if you only have a day and a half to really milk the most out of that day and a half that you have. So thank you again for the food. And yeah, thank you again to Noir Lab because we had the right people and the right spaces so that we could actually be responsive to the needs of the people who were there. Someone had suggested making an introduction room where we could go a little bit more in depth on some introductory topics. And we had the space and the flexibility to do that instead of just saying, nope, this is our agenda, we're going to do it. We weren't limited by that and people had the autonomy and support that they needed. So since it went so well, let's just keep doing it. We want to be able to support even more of these hackathons in the future. We are going to have a little mini hackathon at CMU in Pittsburgh in some amount of time. Also hoping to attach ourselves to other science collaboration meetings and have hackathons maybe that are a little more science focused in a particular area, as well as regional meetings, going to LSST Europe. Maybe we'll come back next year. Yeah. It's lots of exciting stuff that we could do. If the hackathon looked like a lot of fun to you and you want to host us with space and food, then let us know and we might show up. And yeah, just a big thank you to everybody who helped and participated.
Thanks so much, Melissa. Other questions? Yes.
Thanks. I love me a good hackathon. As my esteemed colleague did in the last talk, I have a comment and a question to be a proper astronomer. So the comment is, you may or may not be aware that there's a whole community of people who study how hackathons are done. And they're actually a really cool community to get involved in. You might want to, I can chat with you later if you want about how to get connected to them and how to provide them with useful resources from your hackathons. And then the question is, how did you do group formation? Was it pitches at the beginning or how did you do it?
The group formation was totally organic. People did come in with their kind of pre-canned pitches and going around the room. There were not as many pitches as there were people, which was very convenient. And so we saw that there were, a couple of AGN science related ones. Those people went off into a little corner by themselves and talked about AGNs for a while. And there were also some around like supernova things. And that's what they sound like. Real talk. So yeah, we really didn't have to do very much for those groups to form.
Okay, great. Thank you, Melissa. We're going to move on to the next part of the session. Let's thank Melissa one more time. Okay. Okay, the last thing we're going to do in the time we have left is we would like to do some guided breakout conversations to hear from those of you that are in person in this room and also online to sort of understand what the community's needs are for software going forward. So we've got 3 different groups in here led by some of our discussion leaders from the presentations, the talks. Jeremy Kubica will lead a discussion with the lens from the Link Frameworks. Destry and Adam will lead the lens conversation through Project Dovetail. Meg is going to be welcome to lead the conversation through the lens of the science collaborations, and Melissa will be able to facilitate those that are online together. So we have just sort of a handful of questions here about thinking about the infrastructure, what exists so far, what are those things that are getting right, what are they missing, how much data is going to be needed for the community to figure out what its software needs are starting at 5-year and onwards, when will we know what we need, and how well does the science community understand the compute needs, what can we do to improve that understanding. So if those of you that are in the room would like to sort yourselves into one of the lenses that seems the most appropriate, let's do the Project Dovetail lens sort of in the front right over here, the Link Frameworks group over here, and the back with the science collaborations lens. Yes.
Thank you, Andrew. A couple just logistical questions as we go into breakout discussions. One is, I see that there's about 17 minutes left in the hour. And so what's the ending point? Do people need to be, are we going to talk to the end of the hour? I have to put notes?
So in the shared notes document, if people would be able to record some of our conversations, we'll come back in about 15 minutes, 12 minutes for conversation, so that the last 5 minutes we can share the discussions that we had.
Second administrative question / suggestion, especially maybe for the Dovetail maybe frameworks. Is it acceptable if people just want to have more interactive conversation that aren't necessarily through these specific questions you have offered?
Understood. That these are just starter conversation questions, but you can talk about whatever you'd like with the team that's here. Okay, with that, if we'd like to break into your groups, let's do it.